Welcome to section 8.3. Pause your video, read this screen, and try to get it to make some sense. So first, let's consider what we're talking about. We're in the complex number system in chapter 8. So we're dealing with imaginary numbers. So despite the fact that it looks like it's a regular axis, it's truly imaginary. And so everything we're doing is going to have to change to incorporate this imaginary number. So what used to be the coordinate over A up B is now going to be considered A plus B times the imaginary. To give you just a little bit of theory before we get to our formula, I want to remind you that if this is theta, the cosine would be A over the hypotenuse, which is R. If I were to cross multiply, I would wind up with R times the cosine of theta. Hopefully you can see what's coming next, the sine. So if I'm dealing with the sine of theta, I'd be dealing with B, the opposite, over R, the hypotenuse. And again, if I cross multiply, I'll have B is actually this R times the sine of theta. Now let's put it together with how things need to look in this imaginary plane. A, we just substitute R cosine theta, so there it is. B, we just decided is the same thing as R times sine of theta, so there it is. And there's the I that needs to be part of this new coordinate system. If I factor R from both of these components, here is my new formula. Take a moment and write that down. So if I'm working in this imaginary plane and I'm asked to change something to trigonometric notation, pulling together what we already have learned about our triangles and their ratios, I would know that I would have 1, 1, and Pythagorean theorem would give me radical 2 for the hypotenuse. So if I say that A is 1 and B is 1, then my new trigonometric notation would take the R is going to be the hypotenuse, radical 2, times the cosine of 45, plus I times the sine of 45. This means that using my new formula in the imaginary plane, given this example, separating out A and B, I can change the way it looks. So it's kind of like an identity in some regards, with a different notation, which shows me that these two things are equal. So let's look at these two examples. First thing, identify A and B. Consider where these might sit on a coordinate plane. X is negative. The A represents the X coordinate. The B is positive. So the picture coming out of that might look something like this. And here's my theta. Hopefully you remember your ratios, and if you have a radical 3, then across from that radical 3, you're going to have a 60-degree angle, which means by default, my theta must be a 30-degree angle. But it's not quite that simple because we are in the imaginary plane. So if I apply the formula for the 30, 60, 90 triangle of 1, radical 3, and 2, this side, the hypotenuse side, should be twice as big as my regular side, which was 10, 2 times 10 is 20. This means r is 20. So when I plug in, my formula says r, which is 20, times the cosine plus the sine. But wait, you say, and you're right. 30 is only my reference angle. What's my actual angle? If 30 is the reference, then the rest of this must be 150. So I would have 20 times the cosine of 150 plus I sine of 150. That's in degrees, changing into the imaginary plane. So what if we're just given a 4? The 4 does not have an I, which means A is 4. How many I's do I have? Well, 0 of them. So B is 0. Where does this sit in the coordinate plane? Over 4, up none. So what is R? Well, actually, R is 4. So when we plug in, we're going to get 4 times the cosine of our angle. Our angle here is 0, plus I sine of 0, transferring us back into the imaginary plane. Another example. Given our formula, let's try -5 plus 5i. First, identify A and B. Draw it. A is negative, B is positive. Drop down your altitude to form your reference angle. What type of triangle would make this happen? To get a 1 and 1 ratio, it would have to be isosceles, making my reference angles 45 degrees. But since we are in quadrant 2, my full angle here would be 135 degrees. So when I write this up, to plug into the formula, I also need the R value. R in a 45, 45, 90 triangle is radical 2 times as big as the original. So we would call that 5 radical 2. And to plug into the formula, we would have 5 radical 2 cosine of 135 degrees plus I sine of 135 degrees. We're just changing the way it looks to put it in trigonometric notation, despite the imaginary status. Now let's go the other direction. Given something in trigonometric notation, let's change it to standard notation. When doing this, my hint is to evaluate things first. For instance, what is the cosine of 0? What is the sine of 0? Cosines go with x's, so the cosine of 0 degrees is 1. Sines go with y's, so the cosine of 0 degrees is 0, which means I will have a radius of 3 times 1 when I distribute, and 3 times 0. 3 times 1 is 3, 3 times 0 is 0. This means that A plus BI, as it should be in my answer, is just going to say 3. Another example, evaluating first what's the cosine of 135 and the sine of 135. 135 would be about here. Drop down the altitude for a 45-degree reference angle. If it's a 45, 45, 90 triangle, you have 1, 1, and radical 2, but your x-coordinate is negative, going backward from the x-axis. So the cosine of 135 would be adjacent over hypotenuse plus the sine of 135 would be opposite over hypotenuse. Distribute to solve, and you get negative 4 over radical 2 plus I over radical 2. And if you're thinking to yourself, wait, you can't leave that radical on the bottom, you're right. So rationalize your denominator by multiplying by radical 2 over radical 2 in each instance to get an answer of negative 4 radical 2. Radical 2 times radical 2 is 4 inside a square root. Square root of 4 is 2. And I times radical 2, again, over 2. And one last thing we can do, in the first term, we can reduce for a final answer of negative 2 radical 2 plus 2I radical 2. If you get a situation where your original question is listed in radians, change it over. Multiply by 180 over pi and simplify. If you didn't already know that pi over 3 is 60 degrees, you do now. We are in quadrant 1 with a 60-degree reference angle. Your ratios would be 1. Radical 3 is always across from our 60-degree angle. To help us evaluate that the cosine would be 1 and a hypotenuse of 2. This helps us evaluate the cosine of that 60-degree angle. Here's our angle. Adjacent over hypotenuse would give us 1/2. And the sine of the same angle would be radical 3 over 2. Now recall, that was only the evaluative portion. We actually have to multiply all of that by 5. When we distribute, because of that radius, we're given a final answer here of 5 times 1/2, which is 5/2. 5 times radical 3 is 5 radical 3 times I, all over 2. There's your final answer. Now let's take on one more concept for the day. If we're going to take these complex numbers and multiply them, our formula of two things in trig notation multiplied together becomes multiply the r's, combine the cosines, and combine the thetas of the sines. So let's change this up. First of all, a is 2 radical 3, b is 2. What would that look like? So that means a is your x-coordinate, y is the b. Since a has a radical 3, its angle would be 60 degrees, giving us our reference angle of 30. When that's the case, then our hypotenuse will be twice as big as the small side. So it will be twice as big as 2, also known as 4. So when I set this up in trig notation, I would have 4 times the cosine of 30 plus I sine of 30. Round 2. I. That says that A is nothing. There's no A coordinate because B is what is associated with the I piece. So that would look like this, over none up 2. What's the angle? In this case, the angle of reference would be 90 degrees, and our R is going to be the radius, which is 2. Putting that into R is 2 cosine of 90 plus I sine of 90. So that way we can put it into our multiplication formula, which is going to say 4 times 2 cosine theta 1 is 30, theta 2 is 90, and then I sine of the same sum. for a final answer of 4 times 2, which is 8, times the cosine of 120 plus I sine of 120. So in this problem, first thing I probably want to do is convert pi over 3 to 60 and pi over 4 to 45, showing me I now have 5 times the cosine of 60 plus I sine of 60 times 2 cosine of 45 plus I sine of 45. And using my formula, I would have 5 times 2 cosine of, when you are multiplying, we're going to add the thetas. Again, add the thetas. So my answer would be 10 cosine of 105 plus I sine 105. Make sure you read carefully how do they want the answer. Trig notation, here it is, and I'm done. Happy computing!